काम कर चुके हैं और अभी कंटिन्यू काम कर रहे हैं, उन्हीं का आज लेक्चर है। उत्सुक है सुनने के लिए और बहुत ही इंटरेस्टिंग लेक्चर होगा। वो भी हम लोगों के साथ जुड़ गए हैं। इनका भी काम बहुत ही सराहनीय है। जिस क्षेत्र में काम कर रहे हैं काफी गति रहता है और बहुत ही रुचि से हमेशा सलाह देते रहते हैं और उम्मीद है कि आपका लेक्चर बहुत ही टीचरों के लिए, सबके लिए बहुत ही लाभप्रद होगा। ये भाग्य होगा कि उनका लेक्चर सुनने का मौका मिल रहा है। और एलन इसके बाद प्रोफेसर एलन साहब, जो आजकल तमिलनाडु में बेलोरो यूनिवर्सिटी में प्रोफेसर हैं, उनका भी सुपर कन्वर्जेंस ऑफ सिस्टम ऑफ नॉन लीनियर फंक्शनल वोल्ट्रा इंटीग्रल, दैट इज इंटीग्रल इक्वेशन में इनका काम है, जो कि अप्लाइड मैथमेटिक्स है। अप्लाइड मैथमेटिक्स बहुत इंटरेस्टिंग मैथमेटिक्स होती है। प्योर से तो बहुत अच्छी होती है। प्योर में तो ये समझ में आने में बहुत परेशानी होती है, लेकिन अप्लाइड को हम आसानी से समझ सकते हैं और उसको आजकल ऐसे ऐसे सॉफ्टवेयर बन गए हैं जिसके सोल्यूशन। हाँ, प्रोफेसर रेशमा हमारे ही इसी कॉलेज से, उन्होंने प्रोफेसर पांडे के साथ काम किया है और पीएससी से अभी इनका अपॉइंटमेंट 3 साल पहले हुआ था। और हम लोग भाग्यशाली हैं कि हमारे बच्चे अच्छी अच्छी जगह पे जा रहे हैं और उनका भी लेक्चर होगा। उनका टॉपिक जो है वो इन मतलब ग्राफ थ्योरी में है और डिस्क्रीट मैथमेटिक्स में, जो हमारे बच्चों को, एमएससी के खासकर बच्चों को बहुत ही लाभप्रद होगा, जो कि हम लोग सुनेंगे और हमारे बच्चे काफी रुचि के साथ सिलेबस में भी उनको आगे बढ़ने का मौका मिलेगा। आई रिक्वेस्ट टू सीटी अगिल साहब डिलीवर टू लेक्चर टोपोलॉजी एंड रिलेटेड टॉपिक। थैंक यू सर।
Okay, thank you, sir. Thank you, DP Shukla, sir. First, I am very thankful to this organization for giving me this opportunity. Yes, I am audible. Am I audible? Hello? Yes, okay. Thank you. Yes, sir. Okay. Thank you, sir. Let me share my screen. Just wait. Okay. Today, I have chosen the topic, the topology and related topics. Right now, I am not talking about the research, but I am discussing a very simple topic, that is a topology, its basis, how the basis generates the topology, how we compare the topology, and that much topic we are going to discuss in this today's lecture. The first I will introduce what is a topology. Topology, basically, it is a very simple concept. If we take any non-empty set X and tau is nothing but the collection of subsets of X. It may be all, it may be some, or it may be some finite. Okay. This tau is only collection of subset of X, and if this collection satisfies these three conditions, 1, 2, and 3 condition, then we can say the tau is the topology on X here. The first, what are these conditions? In this collection, empty set and must contained in this collection. It means empty set and X must be is in tau. Second, if we take any collection, what it may be, U alpha belongs to index set, be any collection from this tau, then their union of all these members, that is a union alpha belongs to index set of U alpha, also must belonging to tau. This is the second condition. And third one, if we take any finite member, that is u1, u2 dot dot un from this tau, then their intersection must be belonging to tau. If this collection satisfies these three conditions, then the tau is said to be topology on X here. Okay. So, and the members of topology, which suppose X is a set and tau is the topology on X, the members of this tau, these are called open sets. Okay. The members of all these tau, these are called open set. And what are the closed set? If U is subset of X and U is said to be closed if that U complement must be belonging to tau, or we can say that U complement is open set. Okay, because we have studied what is the open set here, no doubt. Now the simple example we construct here, the simple example of the topological space. One more thing, and if this tau is a topology on X, then the ordered pair X tau is called topological space. This is called the topological space here. Okay. Let's take here, if we take that X with the any set, X with any set, what it may be, non-empty set, and if we take tau is equal to only two members, that is an empty set and X, and clearly only these two members forms the topology on X, because empty set first condition is trivial here, second condition is also trivial, and third one is also trivial here. Okay, and therefore this tau is a topology on X, and which is the smallest one topology on that set, and this topology is called the indiscrete topology on X here. So in this indiscrete topological space, only empty set and X are the open sets. Okay. Let's take another example. If we take X be any non-empty set and tau is equal to power set of X. Okay, power set of X. And this collection also forms the topology on X here. Clearly, because in a power set, empty set and X must belong to power set. And if we take the any collection of the members of P of X, then obviously their union is also be a subset of X. Therefore, this member also belonging to P of X. And similarly for the intersection. And and this P of X is the largest one topology on the set X. And this is called the discrete topological space. And in the discrete topological space, clearly that every subset of X is a open set, as well as every subset of X is a closed set. Why? Because if we take A with the any subset of X, then that A complement belonging to power set, because it is a subset of X. So it means it is an open set. Consequently, that A becomes the closed set. Okay. If we take X be a set containing three elements, and on this set we can define different 29 topologies on X. Yes. Hello.
कैमरा कहाँ चालू कर रहा है राहुल?
Hello.
ऊपर है वो यार, नहीं हो हुआ मेरा.
Yes, any trouble here? Okay. That X is equal to ABC, and these three, 1, 2, 3, we have taken only these three different topologies on set X. So this is the indiscrete topology. You think here, if a set containing only three elements, then we can define the 29 different topologies. So it means we know here R with the infinite set. Then how many topologies we can define on set of real numbers? That is a very interesting question, and we can define the different type of topologies on R, and also we can compare these topologies. We see how we can compare the topologies. So here we have taken here X be a set containing three elements, and we have taken this first collection, and clearly you observe that this collection does not form the topology. Why? Because in this collection there is no empty set and X. Similarly, this collection also does not form the topology because the union of these two members does not continue in this collection. That's why this collection is also not topology. And here also, this collection also not a topology because the intersection of these two members is a singleton set B, and which is not belonging to this one. And so therefore, these three collection does not form the topology on this set. Okay. Now, let X with the any set And tau f. Tau f, we have taken the collection of those subset of X, either whose complement is finite or all of X. And now we will show this tau f, this collection forms the topology on X, and this is called the finite complement topology. And clearly see here that empty set belonging to tau f. Why? Because the complement of empty set in X is X, and it is all of X, and so therefore this empty set belonging to tau f. Similarly, that X belonging to tau f, because the complement of X in X is equal to empty set, and empty set is a finite set, and that's why the first condition is trivial here, that empty set and X belonging to tau f. Similarly, we will check here the second condition here. If we take that any subcollection, that U alpha belonging to index set which belonging to tau f. What is our aim? Our aim is to show that the union of these members, that U alpha index set belonging to tau. That is our aim. But when this union belonging to tau, if and only if its complement is either finite or all of X. And so if we take the complement in X of this collection, that will we denote like this here, that complement of that U alpha belongs to index set of U alpha. And so by De Morgan's law, we can write this intersection over alpha belongs to index set of complement of each of U alpha in X here. And now for simplicity, we are taking here that each U alpha is not U alpha is not X and empty set. And so clearly that each U alpha belonging to tau f, so it means its complement is we are taking finite, and this is the intersection of the all the finite sets. So therefore this is a finite, and consequently this is finite. So it means this union belonging to tau. And similarly, we can show the intersection here. Okay, so if it means U1, U2 dot UN belonging to tau f. Our aim is to show that intersection I varies from 1 to n of this UI belonging to tau f. And this intersection belonging to tau f if its complement in X is either finite or all of X. So we will take here like this here. And by De Morgan's law, we can write this is union I varies from 1 to n of complement of UI in X. And so each of the set, this complement of UI, because these members belong to tau f, so each of the finite set, and what is this? This is the finite union of finite set, so it is again a finite here.
Uninterrupted.
Yes, and so therefore this intersection also belongs to tau f, and this tau f forms the topology, and this is called the cofinite topology or X here. Now, here, if this tau and tau dash, if these are the two topologies on the any given set X, and if tau dash contains tau, okay, tau dash contains tau, so in this case we can say that tau dash is a finer, stronger or larger topology than tau. And on the same time, we can say that tau is the coarser or weaker, or we can say smaller topology than the tau dash here. So these are the comparison part here, that tau dash, because tau dash is a collection, tau is a collection here. And if tau dash is a superior collection than tau, then the tau dash is called, it is the stronger topology than tau, whereas tau is the coarser topology than the tau dash. Now, what are the bases? Because basis generates the topology. So what is the base? If X is the any set, if X is the any set, and script B, again script B is the collection of subset of X. What is this? This is the again a collection of subsets of X. So collection of subset of X, and this collection is said to be basis for X. The script B is said to be basis for X if this collection satisfy one and second condition. Okay, so what is the first condition here? If for each X belonging to X, for every X belonging to X, there exists at least one member B belonging to script B containing X here. Okay. So this is the first condition, trivial condition. That is important condition. That what is here? X with the non-empty set, script be the collection of subset of X, and if for and this script B is to be basis if for each X belonging to X there is at least one member B in this script B that containing X here. And second condition is that if there is some element X which belonging to intersection of two basis element, then there exists another basis element B3 belonging to script B which contains X and which is subset of B3 subset of B1 intersection B2. Okay. So if this condition hold, that first and second condition hold, then this script B, that collection is said to be basis for the X. Okay. So basically is a simple concept. And now if suppose script B is the basis for X, basis for the set X, then we define the open set. Open set, it means member of the topology. Okay. We define the open set if that U is the subset of X and that U, we say that U is the open set. U is the open set, it means U belonging to tau. It means what we are doing here, we are defining the topology tau which is generated by the script B. It means we have the set X, we have the basis, and with the help of this basis we are defining the topology tau on set X here. And the tau is the topology on X, it means we need to define the member of this tau. And so we take those subset of X is in tau that satisfying the following condition. And what is that condition? For each X belonging to U, for each X belonging to U, there is at least one element in this script B which contains X. Okay, which contains X and which is totally contained in U here. Okay, that is totally contained in U. If this condition hold for every subset U of X or in subset U of X, then that U belonging to tau, and then we collect those subset U of X which satisfy this condition, then this tau clearly which forms the topology on X, and that topology is said to be topology generated by script B. Okay, that topology is said to be generated by the script B, and every basis generates a one topology, but different topology can generate the same topology here. So we'll see some examples here. Let X is equal to ABC, and we take here script B is equal to singleton A, AB, and BC. Now we will check whether this collection is the basis or not here. Okay. See here. First condition is trivial here. For element A, there is a singleton set A which contains that A. For B, AB is there. For C, BC is there. It means first condition is clearly hold here. Now we will check for the second condition. If there is an element A which belongs to intersection of these two elements. Okay, but clearly their intersection is itself singleton set A. So it means we are taking here B3 is equal to that A here, and that A fulfills this requirement of B3, and second condition also verified here. Now we will check here for these two basis element, that B belonging to the AB intersection BC, but there is no any basis element B which contains B and which is subset of this intersection, and so therefore this collection is not a basis here. Similarly, you check here. Okay, this is a trivial one example. We will do this one. Now we come to the R2 for the set of real number. We have taken here X is equal to R2, and in R2 we will check. Yes, here R2. Now what we are doing here, we are collecting for element, because every element in R2 has the form like this ordered pair. that x comma y. So we are collecting the circular results. Circular results, it means that we form the one circle about the point x comma y of radius r, and we are taking the interior part of this here. Okay, so it means script b is equal to collection of those x y such that x minus a whole square plus y minus b whole square less than equal to r square, where we have taken ab is the center point, r is the radius. So it means these are nothing but the disk here. Okay, these are the disks, and clearly this disk fulfills the requirement of the basis. So first condition is very simple one, because diagrammatically we can see, because if we take the any element in R2, then we can form the circular regions about that point that containing the center one, and so therefore the first condition is trivial here. The second condition, if suppose there is a one element which belonging to intersection of the two circular regions, then we can form the another one circular region in the common part, and that is the thing, but the basis element containing that one, and which is subset of the this intersection of b1 and b2 here. So here we have taken b1 and here we have taken b2, and we form this radius of this form, and then we can construct b3, and b3 contains the pq1 which is subset of b1 intersection b2, and so therefore if we take the collection of all circular regions in R2, that form the basis for R2 here. Okay. Also, if x is the any set, and if we take script b is equal to collection of all one point sets, then this also form the basis, and that basis generates a very strong topology that is called discrete topology here. Okay. Okay, already we have taken here this how this tau form the topology on x, but we yes, and what is the relation between the basis and the member of tau here? In fact, x is a set, script b is a basis, and this tau is the topology generated by basis. Then what are the relation between the script b and tau here? The relation is very simple, because every basis element is an open set, because every basis element fulfills the requirement of the open set here. Because if we take b here, b is subset of x, and for each x belonging to b, there is a same b which contains x and which is subset of b here. So it means that every b belonging to tau here. So clearly, so it means script b is totally contained in tau. And what are the tau? Then the every element, if we take the u belonging to tau, then clearly that u is nothing but the union of all basis element here. So it means that the relation is that these elements of tau, it means this tau equals the collection of all unions of elements of script b here. So it means that is the relation between the topology tau generated by script b, tau and script b. The members of tau are nothing but the all possible union of the elements of the script b here. This is the then when we have to compare the topologies, that if script b and script b dash, these are the basis for tau and tau dash. Okay, the script b is the basis for tau, and script b dash be the basis of tau dash. Then we have to the following conditions are the equivalent here. So when we say that tau dash is a finer than tau, so it means that the basis element of the tau dash, these are the smaller one. So it means for each x belonging to x and each basis element b belonging to script b containing x, there is another basis element b dash in script b dash which contains x and which is contained in script b here. So it means when we have to say that tau dash is finer than tau, then we need to show this condition, or if this condition hold, then we can say tau dash is finer than tau here. Now on set of real numbers, we are defining the different type of basis. So what is the script b? On script b, if we take the collection of all open intervals ab, and clearly the collection of all intervals, and where that n points a and b belonging to r, this collection forms the basis for r here. This forms the basis for r. Similarly, we can say that if we take the collection of all open intervals where A and B belonging to rational numbers, if we take the n point rational number, this collection also form the basis for R. And one interesting thing is that this basis, when AB belonging to R and when AB belonging to Q, these bases generate the same topology. Same topology. Another example of the basis, that is, we take here B dash. B dash equal to collection of all like this set. As usual sense left side close and usual sense right side open. The half open intervals, that is the usual sense. Okay. This collection of all these members where n points belonging to R, it also form the basis for the R. And this basis generates a very interesting topology that is called the lower limit topology, and usually it is denoted by the notation RL. Okay. And now, so we'll check here what is the relation between the lower limit topology and what is the yes, okay. Lower limit topology is strictly finer than the standard topology. So see here how this is a standard, how it is strictly finer than the standard topology. If we take the any basis element AB in the standard topology, because collection of all open intervals generates topology, that topology is called the standard topology. Okay. That we have taken the basis element in the standard topology containing X, then clearly there is a, because X is here, we can form the basis element like this XB here, XB, which contains X and clearly which is contained in open interval AB. So it means that the basis element of the lower limit topology, these are the small definition here. But reverse condition is not whole. It means reverse how? If we have the like this here, CD, and clearly this is the basis element in script B dash which contains C here. But we cannot generate the open interval that contains C and which is totally contained in CD. Because whenever we have to find the open interval containing C, so we have to go to the left hand side. And if we go to the left hand side to the C, then there are infinitely many elements which does not belong into this interval. That's why this interval does not contain in this one. And so therefore, the lower limit topology is strictly finer than the standard topology here. Okay. I will this one. Actually, I want to compare these one topologies here. The tau one is the standard topology. Arcade topology, it means topology generated by the basis, this one. These are the basis. B1 means collection of all open intervals, and B minus K, it means collection of open intervals minus this K set here. Okay. So it means these are the basis of this form here, that script BK is equal to collection of all open intervals where AB belonging to R, union collection of all open interval AB minus K set. Okay. What is the K set? K set is the that is a set containing elements 1 by n, where n belonging to Z plus. Okay. And topology generated by BK, yet it is called tau K here. Okay. And now here we have to study the what is the relation between this topology, because these are the basis, and basis generated by these are the topologies here. The tau, what is the tau 1? Tau 1 is the standard topology. What is the tau 2? Tau 2 is the arcade topology. Tau 3 is the finite complement topology. This is the upper limit topology. It means which is generated by the basis of, that is a half open interval of this form. And tau 5 is the topology which is generated by the rays here. Okay, left rays. And whenever we have to see this relation, so see here, what is the relation between tau 1 and tau 2 here? So clearly standard topology tau 1 is contained in tau 2 here. Why? Because if we take here the basis element AB in standard topology containing X, and the same, there is a basis element because in RK, basis for RK are the collection of all open intervals as well as including all the set of this form here. And so therefore we can choose the same set containing X and which is subset of this one. And so therefore this we can say that tau1 is contained in tau2 here. But converse is not true here. Converse, it means that I want to say that tau2 is not contained in tau1. Why? Because if we take the one open set like this here, -1, -1 to +1 minus k, -1 to +1 minus k, and clearly 0 is contained in this set here. Okay, because we have subtracted only the k element. We have taken out the element or like this here, 1 by n belonging to z plus. But now 0 belonging to this set, but we cannot construct the open interval because the open intervals containing 0 has this form. But this interval contains many members of the form this one. And so therefore 0 belonging to this set, but this is not contained in this set here, -1 to +1 minus k here. And so therefore this condition do not hold here. And so therefore that tau2 is not contained in tau1. Okay, but tau1 is contained in tau2 here. Okay. Now I will erase this part here. Sir, how much time I have, sir? Hello?
1 minute, sir.
1 minute.
Only 1 minute.
Okay, okay. Thank
Hello?
you, sir. Yes, sir.
Only 1 minute more.
Okay, okay. Thank you, sir. Okay. And using this criteria, we can find or we can realize what is the relation between the different topologies. Okay, and this one relation we will just see what is the relation between the tau1 and tau3. Okay, what is the tau1? Tau1 is the standard topology and tau3 is the finite complement topology on R here. So now, so clearly here that tau1 is not contained in tau3. Why? Because if I take here, because we know that the open interval AB is a open set in tau1. Okay, but this open set AB does not belonging to finite complement topology tau3. Why? Because the
Thank you, sir, very much.
Yes. Okay, sir. Thank you, sir. Yes. Okay. Thank you. But I have. Okay. Thank you, sir. Any question? Any doubt? Any suggestion? Okay. Okay. Thank you, sir.
हेलो,
हाँ. Yes.
आवाज आ रही है क्या सर? हेलो,
हाँ. Yes, sir.
हेलो, हेलो, आवाज आ रही है क्या सर? हाँ, थैंक यू सर. Now, our second eminent speaker, Professor V.N. Mishra. I request to Professor Mishra deliver to lecture topic approximation of signal in Banach space.
Thank you, Professor. Thank you, Professor D.P. Shukla, sir, for kind invitation in this STEAM program. Is it audible to everyone? Okay, sir. Good. Hari Om, Jai Sri Mannarayan to all of you. Good afternoon to all of you. I am very much thankful to Professor and Head Convener of this prestigious program, Professor Dr. D.P. Shukla, sir.
Thank you,
Department
sir.
of Mathematics, Department of Mathematics and Computer Science, and Government Model Science College, Rewa, MP, and competent authority of this prestigious program, that is National Seminar, Recent Trends in Mathematics and Computer Science, organized by Department of Mathematics and Computer Science, sponsored by Department of Higher Education, RUSA, and World Bank scheme MPHEQIP under FDP
अच्छा बोल रहे हैं
during 9th and 10th January 2023. And this is a common platform through which we can share our ideas in the our ideas in this common platform, so that every researcher and a teacher can get benefit from this prestigious program. And so here since this program is celebrated, that is on 135th birth anniversary of Srinivas Ramanujan, and Srinivas Ramanujan was the famous mathematician, and having deep faith in his Kul Devi, and यथा शिखा मयूराणाम नागाणाम मणियो यथा तद्वद वेदांग शाखाणाम गणितम मूर्धनि स्थितम. As peacock in climax, that is peak is famous in peacock, and naganam madiyo yatha, there is muddy in snakes. Muddy in snakes is famous. Like the same way, mathematics is the queen of all sciences and all Vedas. There are some branches of Vedas in which the mathematics is at the peak. And through mathematics, we can enhance our Manomay Kosh, Vigyanmay Kosh, Anandamay Kosh. Through proper diet, we can strong our Annamay Kosh. And through proper pranayam, breathing exercise, we can strong our Pranamay Kosh. And through our intellectual power and imagination power and problem solving skill, we can strong our Manomay Kosh, Vigyanmay Kosh, and Anandamay Kosh. So these are the koshas in our sciences. Three bodies: Sthul, Sushma, Karan, and Pancha Kosha. Here we will discuss some basic concepts of mathematical analysis, and through mathematics, everything is not possible, anything not happening. Mahaviracharya also said, Bahuvir Plapai Kim Triloke Sacharachare Yat Kinchit Vastu Tat Sarvam Gaditen Vinana Hi. Means Gaditen Vinana. What is the deliberium to mathematics? What is the deliberium to mathematics? No object in this universe is without mathematics. No object in this universe is without mathematics. Means mathematics is the science which used in our daily life program. That is from morning to evening till sleep time. It is used in our daily work. Through mathematics, that is, we can take anything. We can take anything from any shop, then we can pay the required money to the shop and take the object, take the thing. There is also mathematics. If we make a tea, then how much spoon tea required, how much spoon of sugar required, there is also mathematics. And mathematics is the daily routine in our life. Mathematics is the mathematics which is used in our daily routine life. So here we can start my presentation here, something basic concepts of functional analysis, real analysis, complex analysis. So I am sharing my screen here. Is it So through mathematics, everyone can become balanced in his life, because mathematics teaches us discipline also. Discipline also in our life. So let us see here, that is some basic concepts of mathematical tools, that is approximation of functions by using positive linear operators, etc. In this talk, if time allows us, that we discuss the degree of approximation of signals, functions. Every signal is a function, but every function need not be signal. Using various types of summability transforms, more methods in different spaces, approximation of functions by positive linear operators using quantum calculus. Q calculus will also be highlighted here. And during this talk, few applications of approximation of functions will also be highlighted here. And these are the subsequences. Suppose yes, and T are two sequences in a set capital X. Then T is said to be a subsequence of S if there exists a mapping phi from N to N such that T is equal to S composition phi. T is equal to S composition phi. And for each n element of capital N, there exists an element M in N such that phi I is greater or equal to N, for every I is greater or equal to M in N. In other words, we say that if Sn is a sequence in X and In is a sequence in N, such that I1 less than I2 less than I3 and so on so forth less than, then Sin is also called a subsequence of Sn. Suppose S is equal to 1 upon N is sequence in R. That is 1 upon 2, 1 upon 3, 1 upon 4 is sequence in R. Then what is the subsequence of it? Well, that is 1 upon 2n minus 1 is subsequence of it. Because if we define phi from n to n such that phi n is equal to 2n minus 1, then Tn is equal to S composition phi at n. And S of phi n is equal to S 2n minus 1 is equal to 1 upon 2n minus 1. That is Tn is equal to 1 upon 2n minus 1. Means if putting the values of n is equal to 1, 2, 3, 4, then we get 1 upon 3, 1 upon 5, 1 upon 7, etc. Is a subsequence of sequence 1, 1 upon 2, 1 upon 3, 1 upon 4, etc. And approximation by summability technique, that is approximation, especially Fourier approximation and wavelet approximation, have received a great importance during the last few decades because of their use in modern technology, with signal theory, data compressions in particular, and Fourier approximation was originally evolved from the problem of divergence of Fourier series. Kolmogorov in 1926 has proved that Fourier series of a continuous function of period 2 pi can diverge almost everywhere. And thus summability theory came into its appearance. In summability theory, we attempt to assign suppose smallest to an infinite series, that is, we try to generalize the concept of sum of any non-convergent series. That is, Fourier series of a continuous function of period 2 pi can diverge almost everywhere. So any property P is said to hold almost everywhere, provided the measure of that set is which the property P does not equal to true. That is set of measure 0. That is called a property almost everywhere. And summability theory, the theory of assignment of limits, which is fundamental in analysis, function theory, topology, and functional analysis. In mathematical analysis, a summability method is an alternative formulation of convergence of a series which is divergent in the conventional sense. Summability is a field in which we study the non-convergent series, non-convergent integrals, and assigns a value number to it. For instance, following are the some interesting cases for which the assignment of limits can be done. Real or complex equations are the limit process as limit and tending to infinity. And the sequence and series of functions like power series, Fourier series, etc. Sequences and series of functions like power series, Fourier series, etc. In 1890, Cesaro was one of the mathematicians who gave Cesaro filter. And Cesaro deal with the sum of some divergent series and defined Cesaro summation. In a specialized mathematical context, values can be objectively assigned to certain series whose sequence of partial sums diverges. This is to make the meaning of the divergence of series. For example, this is the Grandi series, that is 1 minus 1 plus 1 minus 1 plus 1 minus 1, etc. And if we apply Cigaro summation to this infinite series, that is it is Cigaro summable to finite number 1 upon 2. Okay, finite number 1 upon this is neither convergent nor divergent, but it is Cigaro summable to finite number 1 upon 2. Okay, it means that when the method of convergence or divergence fails, then one branch of mathematics, that is called summation type of operators, approximation by summation type of operators, approximation by summation integral type of operators, arise in the literature of mathematics. And its place is a very significant role to approximate the function and gives the best solution, stable solution, existence of the solution. Okay, there exist three types of summability process: ordinary, absolute, and strong summability. And summability techniques are very much applicable as a tool for the filter and the signals in the form of series, infinite series, Fourier series, wavelets, etc. using the various summability methods such as matrix, Cigaro, generalized, Holder, harmonic, Risch, and typical means, Nalund and generalized and Nalund indexed is Abel, Euler, Borel, Hausdorff, Monarch, etc. The aim of this study is to discuss the stability of the system using the summability and absolute summability methods. By using the advanced summability methods, we can improve the quality of digital filter. By using the advanced summability method, we can improve the quality of digital filters. That is, we can reduce the echo plus noises and get the best approximation. That is, output is best. Output is best means that reduces the echo plus noises. And this is the process of filtering process, that is designing of digital filters with finite impulse and response particular. The approximation of the signals with the help of summability method is widely used in the digital filters such as finite impulse response particular, FIR filters, and infinite impulse response filters, IIR filters. And these filters have numerous variety of applications like in speech and signal processing, communications, radar, sonar, and medical and signal processing, etc. For an engineering problem having piecewise finitely differentiated data with jump discontinuities, there are more sophisticated ways to use the sampled data to obtain a more accurate solution using approximation of Fourier coefficients by summability techniques. There is a Gibbs phenomena in Fourier approximation, that is convergence of Fourier series is very slow near the point of discontinuity. That is, we try to generalize, that is the Gibbs phenomena. Gibbs phenomena is an overshoot, a peculiarity of the Fourier series and other eigenfunction at a simple discontinuity. And this jump discontinuity is also countable. With the help of minimal set of sufficient conditions for a soft computing model, the error can be minimized by using summability methods so that the output data is filtered and according to our interests or observing the behavior and the requirements of the modeled problem. There are various types of summability processes. Toeplitz was the first to put such methods systematically, and thus after his name they are called as T methods. T methods are based on the formation of an auxiliary sequence Tn defined by sequence to sequence transformation. Tn is equal to sigma k is equal to 0 to n an k sk. N varies from 0, 1, 2, 3, etc. and k varies from 0 to n, where Sn is the n plus 1th partial sum of infinite series sigma un. If Sn is the input sequence of informations and Tn is the output sequence of informations, then T is equal to Ank behaves like as a designing of digital filters. Toeplitz matrix behaves like as a digital filter. And T is equal to Nk be an infinite lower triangular matrix of real or complex numbers. Tn is also called as linear mean or matrix mean of the sequence Sn. An infinite series sigma un is summable to a finite number S by T method if limit n tending to infinity Tn is equal to S. where S is a finite number. And the matrix T is said to be regular if limit n tending to infinity Sn is equal to S implies limit n tending to infinity Tn is equal to S. Means the matrix, the method T is said to be regular provided Sn converges to S implies Tn also converges to S. Okay. If the method, any method matrix method T is said to be regular provided Sn converges to S implies Tn also converges to S by applying the same method, that is T method. And the necessary and sufficient condition for the regularity of the appraised matrix T is equal to Nk are this. These conditions are known as Silbert-Paplich-Mann conditions. Silbert-Paplich-Mann conditions. First condition is uniformly summable rows. First condition, that is sigma k is equal to 0 to infinity mod Ank is less than m, where m is independent of n for every n. This is uniformly bounded summable rows, is known as uniformly bounded summable rows. And limit n tending to Ank is equal to 0 for each k, that is terms of any column tends to 0. And the third condition, limit n tending to infinity sigma k is equal to 0 to n, Ank is equal to 1. This is the row sums is equal to 1. This property is known as row sums is equal to 1. Okay. These are the three conditions. That is one superhit example. One superhit example of triplet matrix T is equal to, that is A sigma n is equal to 1 upon n, 1 upon n, for 0 less or equal to k less or equal to n, and 0 for k greater than n. Okay. For 0 k greater than 0. That is also uniformly bounded summable rows, and in terms of any column tends to 0, and the row sums is equal to 1 also. Hold good. So that this here it is. This satisfies this matrix T is equal to Nk is equal to 1 upon n for 0 less or equal to k less or equal to n, and 0 for k greater than n. Satisfies these three conditions. And the sequence 1 upon n is convergent sequence and belonging to C0 space. That is space of all sequences converging to 0, C0 space. But it is not in LP space because the members of LP spaces are convergent, while sigma 1 upon n is divergent. While sigma 1 upon n is divergent, why? Because p is equal to 1. By P series test or any Cauchy general principle of convergence criteria for infinite series, or Cauchy root test, or Cauchy integral test. There are several tests to check that is series sigma 1 upon n is divergent, while sequence 1 upon n is convergent, and the limit point is 0, C0, belonging to C0. This is the matrix analysis. That is, you know that very well, Banach contraction principle. Every contraction mapping on a complete metric space has a unique fixed point. In order to prove Banach contraction principle, we form the iterated sequences. Like in a similar way, these are the iterated sequences formed here. Tn is equal to sigma k is equal to 0 to n, Ank Sk, k varies from 0 to n, and T0, T1, T2, T3, and so on and so forth, Tn, and so on and so forth. These are the iterated sequences. Like in a similar way, for example, in proof of Banach contraction principle, like similar way, these are the iterated sequences. And these are the equations. If we write these equations in matrix notation form, the left hand side will be column matrix T0, T1, T2, T3, and so on and so forth, Tn, and so on and so forth. And this is the lower triangular matrix. And the right hand side is your also column matrix S0, S1, S2, S3, and so on and so forth, this much. So this is the Sn is the input signal sequence, and the Tn is the output desired signal sequence. And this T is equal to Nk behaves like as a designing of digital filtering process. That is receiver and transmitter. Transmitter is obtained by reducing the echo plus noises and gives the best approximation. Trigonometric approximation plays a very significant role in the solution of various physical problems, and its applications are of vital importance. Have been found in telecommunication engineering as well as stochastic analysis problems also. And these are various operators obtained from by assigning different values of Anks, we get different type of filters. This is called as Narlund filter and Cesaro filter. For detail of Cesaro filter, you can visit a book that is Trim Series Text and Reading in Mathematics by Rajendra Bhatia. Fourier series by Rajendra Bhatia, published in Hindustan Book Agency. Hindustan Book Agency. And these are the CRO operator. This is the definition of CRO operator. CRO operator of order delta. Alpha, or CRO operator of order alpha. If nk is equal to this much, en minus k alpha minus 1 upon el alpha for 0 less or equal to k less or equal to n, 0 for k greater than n, where en alpha is given by in terms of binomial coefficient and in terms of gamma function, then the linear mean Tn reduces to zero mean of order alpha, that is C alpha, in general sigma n alpha. And in finite series, sigma un is said to be C0 summable to a finite number s if sigma n converges to s agent tending to infinity. This is the infinite series. See here, sigma n, it is C0 summable to 1 by 2. Because if we apply the definition, S1 is the first partial sum, 1, S2, 1 minus 1, 0, S3, 1 minus 1 plus 1, again 1. And C1 mean general Tn is given by S1 plus S2 plus so on so forth plus Sn divided by n. Okay, arithmetic mean of sequence of partial sums, or we can say that average of partial sums of infinite series, that is C1 mean. If n is even, n is equal to 2m, then Tn is equal to S1 plus S2 plus so on so forth plus S2m divided by 2m. It is equal to 1 upon 2 also. And if n is odd and n is equal to 2m plus 1, that is Tn is equal to S1 plus S2 plus so on so forth plus S2m plus 1 divided by 2m plus 1. And as m tending to infinity, this is also 1 upon 2. Simple calculation. I am not going to explain detail of this calculation because due to less time. If anybody is not getting, please contact me. I will explain in detail. And therefore, we can say that the number 1 upon 2 is assigned to the series in sigma minus 1 to the power n. In other words, we say that sigma minus 1 to the power n is C1 summable to finite number 1 upon 2. Okay, this is the similarly a number 1 upon 4 is assigned to the series sigma minus 1 to the power n into n plus 1. Of course, it is C2 summable but not C1 summable. In general, we can say that sigma minus 1 to the power n plus 1 into n to the power k is Ck plus 1 summable but not Ck summable. Minus 1 to the power n plus 1 into n to the power k. The Ck plus 1 summable but not Ck summable. This is the other example, Nalund method, and this is the example of non-regular summability method, which has been taken from a paper of Professor Prem Chandra, published in Journal of Mathematical Analysis and Applications, Elsewhere Journal, 2002 problem, and title is Trigonometric Approximation of Functions in LP norm. Other method, other operator is Risch operator, and the next is Fourier analysis, Fourier series. Suppose f is periodic signal, and period is 2 pi, and it is Lebesgue integrable in comparison of in place of Riemann integrable. Lebesgue integral because convergence properties might be better for the Lebesgue integral function. Okay, we had taken the signal is integrable in the sense of Lebesgue, not Riemann, because convergence properties for Lebesgue integrable is better, might be better than in comparison of Riemann integrable. And every square summable function, second thing, that is every square summable function on unit circle having unique Fourier series converging to the original function under L2 norm. And the basic fact that is the space of Riemann integrable is not closed, not compact, that is not closed under taking the limits, which makes the analysis hard to do, while the space of Lebesgue integrable functions is closed and complete, compact, complete, so which allows to take the advantage of the fact that, for example, smooth compactly supported functions are dense in LP spaces. So we can
A0/2
all this type of analysis. My voice is audible or not, please? आवाज आ रही सर? हाँ, okay. All this type of analysis is impossible in small space of Riemann integrable functions. So here we take that is suppose f is periodic
3 minutes
function.
more, sir.
Sectionally
3 minutes
continuous.
more.
Pardon?
Only 3 minutes.
How much time, sir? How much time remaining?
आवाज आ रही है क्या सर? आवाज आ रही है? हेलो?
हाँ, आ रही है.
हेलो, आवाज आ रही है सर? मिश्रा सर?
हाँ जी, आ रही है.
हेलो?
आ रही है सर, आ रही है. Okay. Thank you. That is if a periodic function having period 2 pi and Lebesgue integrable as left and right hand derivative of the function at each point of the interval over minus pi to pi, then the Fourier series of f be convergent except the point of discontinuity. Suppose x0 is the point of discontinuity on which the series sum is
टाइम. हाँ देखो, हमारी आवाज आ रही है क्या? हेलो? आ रही है?
that is 1/2.
हेलो?
Limit extending to x0 minus limit extending to x0 plus of fx. Okay, this is the criteria. That is a0/2 plus sigma k is equal to 1 to infinity. This is the Fourier series, and we approximate the function by fx.
Yes, sir.
The constant a, k, b, k are called Fourier coefficients. And conjugate series of Fourier series given by this equation 3. And it is known that the series conjugate to Fourier series is not itself a Fourier series. Because sigma n is equal to 0 to infinity cos n theta upon log n plus 2 is a Fourier series, but the corresponding sine series is not a Fourier series. Hence, a separate study of conjugate series of Fourier series justified here. There are two types of kernels appear in Fourier approximation. One is Dirichlet kernel and the other is Hare kernel. Dirichlet kernel appear in partial sum of Fourier series. And the pointwise convergence of the partial sum of Fourier series is one of the hardest result in mathematical analysis. That is known as correlation-Hunt theorem. And if we define here partial sum of Fourier series, that is a0/2 plus sigma k is equal to 1 to n, ak cos kx plus bk sin kx. This is trigonometric polynomial of order n. And after putting the values of a0, ak, bk, then there is one type of kernel appear here, that is dnt, that is called Dirichlet kernel. And the Dirichlet kernel is even function of t. If we replace minus t in place of t, then dn minus t is equal to dnt. dnt remains the same, so that it is called as even function of t. And if we determine the area of Dirichlet kernel between 0 to 2 pi, that is definitely integral 0 to pi dnt dt is equal to pi by 2. That is area of Dirichlet kernel bounded by t is equal to 0 to t is equal to pi, then we get pi by 2 area, pi by 2 square units. Similarly, nth partial sum of conjugate series of Fourier series, that is denoted by Sn tilde fx, and Sn fx minus fx is given by this much. And pointwise convergence of Fourier series, that is Fourier series of f at x will converge to fx if and only if limit n tending to infinity Sn fx minus fx is equal to 0. This is the necessary and sufficient condition. And if element of L2T means square integrable function, the norm converges by that is by Hilbert space theory, norm Snf minus f under L2 norm tending to 0 as n tending to infinity, as n tends to infinity. This is the norm convergence. Pointwise convergence by correlation theorem, Snf converges to fx almost everywhere x. And if element of L1T means simple absolute integrable function, absolutely integrable function. L2T means square integrable function. Little L1T means absolutely summable sequences. And little L2T means square summable sequences. So f element of L1T, the norm convergence, that is there exists a function f element of L1T such that Snf does not converge to f in the L1 norm. This is because the L1 norm of Dirichlet kernels are not uniformly bounded. And point-wise convergence, Kolmogorov constructed an explicit counterexample of L1 function whose Fourier series diverges almost everywhere. And Dini's criterion also says that at any point x0, Dini criterion hold, then Sn fx converges to fx0 again tending to infinity. And there is jump discontinuity also. Localization property also. Yes, sir.
Hello.
Yes, sir. Why is he audible? Please. Ariava, sir, give the phenomena so that the partial sums F over suit F at the jump point by approximately 9% of the jump at x0, fx plus 0 minus fx minus 0. And the point-wise convergence of the partial sum of Fourier series of F element of LP space is one of the hardest results in mathematical analysis. In 1966, L. coordination proved that F element of L2, then the partial sums converges to F almost everywhere. And in the discrete case, for all F element of L2T, Snfx converges to Fx almost everywhere X element of T. And in the continuous case, for every F element of L2T, SRfx converges to Fx almost everywhere X element of R.
Mr. Sir.
And 1968, Hunt extended this result to LP function for one less than P less than infinity. Yes, sir. More time allowed or not?
Not.
Time heavy. टाइम नहीं है सर ठीक है
सर
जी जी ओके सर होम नहीं ओके पूर्णाहुति कर देते हैं 1 मिनट में पूर्णाहुति कर देता हूं
जी थैंक यू सर
1 मिनट में पूर्णाहुति कर देते हैं थोड़ा सुनिए सर तो आई एम वेरी मच थैंकफुल टू ऑल द पार्टिसिपेंट्स who listen this lecture carefully. If anybody has any type of difficulty or any doubt, please ask me without any hesitation. I am very eager to answer your questions also. किसी को कोई क्वेश्चन है?
Sir, thank you very much.
कोई प्रॉब्लम हो?
Your lecture is very excellent.
सर एक मिनट दीजिए थोड़ा बोल दूं आपके विषय थोड़ा बोल दूं तो ठीक है सर हूँ नहीं कृतज्ञ न कभी मैं द्रोह न मेरे उरावे गुण ग्रहण का भाव रहे दृष्टि न दोषों पर जावे ओम पूर्णमदः पूर्णमिदं पूर्णात् पूर्णमुदच्यते पूर्णस्य पूर्णमादाय पूर्णमेवावशिष्यते ओम शांति 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 हरि ओम श्री गुरुदेव हरि ओम ओम नमामि हरि परम ओम नमामि गुरुम परम मतलब ये भी पूर्ण है वो भी पूर्ण है जो भी दिखता है सब पूर्ण ही है पूर्ण में पूर्ण जोड़ने पर पूर्ण ही रहता है पूर्ण में से पूर्ण निकाल लेने पर पूर्ण ही शेष बनता है तो जो विशिष्ट अनंत के में है वही विशिष्ट जो है शून्य में भी है तो आप सभी को बहुत बहुत धन्यवाद जो आप लोगों ने हमारे को ध्यानपूर्वक सुना और जो है हम आई एम वेरी मच थैंकफुल टू कॉम्पिटेंट अथॉरिटी ऑफ दिस prestigious national webinar. This gives a common platform through which we can share our ideas and our concepts, our mystery, rahasya, so that we can enhance our knowledge through in my teaching as well as in my research as well as industry people can also. ओम संग अच्छम संग दद्धम संग मनासि जानताम देवा भागम यथा पूर्वे संजानाना उपासते मींस ऐसे प्रोग्राम करने का मतलब क्या है लेट अस मूव टुगेदर लेट अस टॉक टुगेदर लेट अस थिंक टुगेदर लेट अस वर्क टुगेदर लेट अस अंडरस्टैंड टुगेदर दैट इज मूविंग टुगेदर थिंकिंग टुगेदर वर्किंग टुगेदर लिसनिंग टुगेदर तो हमारे देवताओं में भी ऐसा गुण रहा है इसी कारण वे पूजनीय है तो ऐसे प्रोग्राम करने से हमारे क्या होते हैं हम अपने नॉलेज को बढ़ा सकते हैं बहुत बहुत धन्यवाद प्रोफेसर डीपी शुक्ला सर जी and other competent authority who gave me the opportunity that is chance to interact with you all. Thank you. Hari Om. Jai Sri Narayan.
Thank you, sir.
Namaskar.
Your lecture is very useful for all participants. And my third speaker, Dr. Reshma Khan, Professor, Department of Mathematics, Government College, Suni. Now topic of tree and discrete mathematics and its application. I request to Professor Khan deliver to lecture
Thank you, respected sir. Very good afternoon to all the participants, those who have joined directly or indirectly to this national webinar. I, Dr. Reshma, today takes this opportunity to present this lecture entitled Trees and in Discrete Mathematics and its Application. First of all, I would like to thank my research guide and all the mentors, those who have supported me a lot and provided this golden opportunity to present this lecture today. Am I audible?
Yes,
Yes,
ma'am.
ma'am, you are audible.
Thank you, thank you, thank you. Let me present. I have topic for today's webinar is recent trends in mathematics and in computer science. I have taken this topic, trees in discrete mathematics. Still, I think it is not. Screen is visible?
Yes, ma'am,
Okay.
yes, it is visible.
Okay, thank you.
Yes, madam.
Okay, thank you, sir. Today we have taken this topic, trees in discrete mathematics and its applications. These are the topics which we will cover today, starting with the definition of vertex and edge, and what is nature of tree in real life in discrete mathematics, what actually is tree in discrete mathematics or in data structure, some examples with its terminologies and with its properties and applications. So starting with the definition, these are very basic words, vertex and edge, a generalization of simple concept of a set of dots or vertices, links or edges or arcs. I think this is a simple dot which we are used to see this here. This is vertex. Sometimes we may call it as points or nodes. And when we join two or more than two vertex, links between these are called as edge. So this is a type of representing the vertex and edge, and its representation as graph. It is given by G, which is the collection of set of vertices, and which is denoted by V, and the set of edges. That means in graph we have two sets, set of vertices and set of edge.
क्या चाहिए और बेटा?
This is the nature view of tree. In general life, we see the trees as roots at the base and then branches and then leaves.
छोटा वाला पैकेट खोली हो वो तो खत्म हो गया था ना
People are not putting their mics off.
Please mute yourself
हाँ.
and the other person
Okay.
speaking.
These are trees in discrete mathematics. We used to take trees root at the top sometime, and then its branches and then its leaves. So now, what is tree? Tree is a connected graph which is never have any circuit or multiple edge or loops. So we can see here an example of tree. It is having vertices as A, B, C, D, E, F, and the edges or links which are connecting them, they are called as edges. Here we see that there are no circuits, no loops. Loops means कोई भी वर्टेक्स ऐसा नहीं है जो कि एक वर्टेक्स को खुद से कनेक्ट कर रहा होगा. Similarly, what are multiple edges? Multiple edges means in between two vertices there will be never more than one connectivity. These are parallel edges also. Sometimes we call it as multiple edges. So tree doesn't have these multiple edges. Therefore, we can say that tree is a simple graph. Simple graph, that means such type of graphs which are never having parallel edges or loops, etc. So we can say that an undirected graph is a tree if and only if there is a unique simple path between any of its vertices consisting of nodes and with a parent-child relations. Some examples of trees. We see that there is a tree with a single vertex. It is also called as degenerate tree. Tree with 2 vertices. Similarly, tree with 3 vertices, 4 and some more trees. One thing we can observe from these examples that any tree who are having n vertices, they always have n minus 1 edge. So this is one of the property of tree which we will see later. These are some examples. Sometimes we have food choices, as in some other countries. And these are types of organisms which we are representing it as a tree structure. Such like organisms, they are plants and animals. Plants can be subdivided as whether in trees or flowers, or trees may be subdivision as having a deciduous trees or evergreen trees. Similarly, for the animals in invertebrate and vertebrate divisions. Moving next, we will see some of the graphs which are whether they are trees or not. So we can say that first example, this one, whether it is a tree. I hope those who are seeing it is fully connected and there are no circuits and no loops, so we can say that yes, it is a tree. Similarly, in example 2, we see that this tree is having 2 parts. So we can say that it is disconnected. So we can't see that say that it is a tree. It is a disconnected. So this is not a tree. Third one, whether it is a tree or not, this is not a tree because there is a cycle which is present in this structure. Similarly, fourth example, yes, we can say that it is a tree because it is fully connected and no cycles, no circuits are present. This is important part of these are tree terminologies. We can see here that at the top of this tree, root is present. This is the basic node or root, which we can also call it as a tree. Firstly, we will see that this A, it is having 2 subparts, एक B से and then from C. So we can see that there are different levels also. There is a height of tree also. Water. Here we can see that अगर हम इसको family tree से compare करते हैं, then we can see that here it is an ancestor part and these are the parents part. And then moving further, we see that these are the childs. D and E here are the childs of B. Similarly, we can say that G and F are also child of C. And also D and E are the siblings. That means they are the same member family. And similarly, G and F, they are also siblings for C. And further, we can see their subdivisions. And at last, we say that K, L, M, and O, P, they all are leaf nodes. That means they are the terminal part of this tree. How we can find the height of a tree? By seeing these levels. For example, we need to find the level of J, at which level it lies. From root node, we will try to count as many edges as it has. So we can say that from A, we move to C, then to F, 2 edges, and then this 3. Total 3 edges lie in between these part from A to J. So we can say that J lies on the level 3. Similarly, we can find different levels and height of a tree. Moving next, what is forest? Forest, actually, this is a collection. There are so many collections of trees. When we are having different components as a tree, then those collections, they are called as forest. That means graphs containing no simple circuits that are not connected, but each connected component is a tree. We can see here the examples of forest. First part, there are 2 trees. They are also collection, more than one. And similarly for the second part, that is also the connected components, and this connected components in group is called as forest. Moving next. What is a rooted tree? Rooted tree also plays a very important role. It is a tree in which one vertex has been designated as the root, and every edge is directed away from root. That means root we represent it by sometimes by encircling that or sometimes entangled that part which is different from all other vertices present on that tree. So a rooted tree is a tree in which one vertex has been designated as a root and every edge is directed away from that part. It has root, parent, child, sibling relations between the vertices. That means similarly, as we have seen on the previous, that there are different levels and heights from which we can decide that which are the ancestors part or the parent part or the child part or the siblings or the root nodes. Moving next, what is a spanning tree? A spanning tree is it's a type of tree which is consisting each and every vertex of the given graph. So, given a connected undirected graph on the examples, it is a spanning tree of that graph is a subgraph. That means it is a part of the same graph, that is tree, which connects all the vertices together. Whenever we are taking a spanning tree as a subgraph of the given graph, we should remember one thing, that all vertices must present all the times. Here in this example, this is a graph which is having 4 vertices A, B, C and D. So a spanning tree, we can see all are the examples of a spanning tree and they all have all 4 vertices present at a time. We should not leave any of the vertices. That means skeleton must be same as the given graph. So this is also one spanning tree. This is also connectivity of edges are changing, but vertices are always same as the given graph. I hope you are getting. Sometimes we can also say that a spanning tree is also a tree. We must never quit any of the properties of tree from that. And these are the maximal subgraph or maximal subtrees of the given tree. Moving next. What is minimum spanning tree? That means we have to find out the spanning tree which are having the minimum weight or minimum cost. So there are 2 algorithms to find this spanning tree which are minimum. The one is Prim's algorithm and second one is Kruskal's algorithm. I hope all students, those who are pairing or pursuing MSc, they are the important topics for them and they are having the huge applications in many parts. These are the Kruskal's algorithm. This is given a network. From this given network, firstly we will choose the shortest edge or the edge which is having the minimum weight and so on one by one. One thing we should remember that never it will have any circuit or closed figure, and moving on the next step one by one, we will repeat until we will have this minimal spanning tree. Similarly for Prim's algorithm, these are the properties. By observing all the definitions and some types, we can see that these are the properties of a tree. In any tree, there is always one and only one path between every pair of vertices. That means whenever you will see any tree, any vertices, any pair of vertices, we can see that only there is one and only one path between every pair of vertices. And second property, any connected graph which is having n vertices, they will always have n minus 1 edge. That means you can draw randomly any tree. We can see here that if we are drawing this tree, 1, 2, 3, 4 vertices, 5, 6, 7 and all, we can count directly that 1, 2, 3, 4, 5, 6, 7. If there are 7 vertices, then it will have only 6 edge. That means n minus 1 edge. And always we can see that between any pair of vertices, there is one and only one path. Next property. A tree with n vertices always have n minus 1 edge. We have discussed earlier. And graph is tree if and only if it is connected, or also we can see that say that a graph is a tree if and only if it is a minimally connected part. Minimally connected, that means it should never have any parallel edges, no circuits, no more than one path on that. These are the applications. There is huge applications nowadays of trees. We can see in how we can store hierarchical data like folder structure, organization structure, family relations. We can draw a family relation tree, or we can store hierarchical data, folder structure. As an example, we can see our in our PC. If we are opening that C drive, there are that is one folder, and inside that there are so many subfolders and then subparts are there. So we can see the examples of folder structure, hierarchical data, and family relations. Even we can draw a family relations in a tree of our family also, of some administrative blocks family also. There are so many examples for family relations. Binary search tree, this is having important application. This is a tree which allows fast search and inserting or deleting on a sorted data. It also allows finding closest item, and trees as models. Sometimes game tree also, decision trees in machine learning algorithm. On yesterday's lecture, our one eminent speaker, that was he has given the detailed about machine learning algorithm. And heaping is also an important type of tree data structure which is implemented using arrays and is used to implement in priority queues. Syntax tree, sometimes in discrete mathematics we are discussing about expression trees also. So syntax trees using for scanning or parsing or generation of code and evaluation of arithmetic expressions in compiler designs. In servers, domain name servers, and a tree connected network, and in a tree topology. There are so many other examples also or applications.
हाँ रेशमा, थैंक यू।
ओके सर।
हेलो, बहुत अच्छा, आपका लेक्चर बहुत ही सराहनीय रहा। हम लोग काफी गदगद हैं और काफी रुचि से सुने भी, और हमारा आशीर्वाद आपके प्रति रहेगा कि आप और ऊंचाई पाएं, ये मेरी इच्छा है। और सभी लोग बैठे हुए यही कह रहे, रेशमा बहुत अच्छी लड़की थी, तुमने कहा उसको अच्छी लड़की का फल तो मिला ही।
That's just, आप सबकी सर ब्लेसिंग्स है, आप लोग ने हमेशा सपोर्ट किया। आई होप इसलिए आज
बिल्कुल किया। देखिए, आप अमरकंटक में एक बार आपको याद होगा हमसे मिले थे और कितना आनर आपने दिया था, तो हम बार-बार उस बात को रिपीट करता हूं। और हमारा यही आशीर्वाद है कि आप हायर ऊंचाई में जाएं। तो क्या आप डिस्क्रीट मैथमेटिक्स वहां देख रहे हैं क्या?
सर कॉम्प्लेक्स भी ले रही हूँ, डिस्क्रीट मैथमेटिक्स भी ले रही हूँ।
और आप इसमें जाइए ना, आप टोपोलॉजी, फंक्शन एनालिसिस, रियल एनालिसिस तरफ जाइए।
ओके सर, ओके सर, नेक्स्ट टाइम आई विल डू। थैंक यू सो मच सर, थैंक यू सो मच।
हाँ, नाउ प्रोफेसर रेशमा खान का जो लेक्चर था वो बहुत ही इंटरेस्टिंग था, बिकॉज एमएससी पीजी क्लासेस के छात्रों के लिए काफी हितकर था, और सभी कई छात्र हमारे जुड़े हुए हैं जिनके लिए ये लेक्चर बहुत ही लाभप्रद होगा, इनके लिए सिलेबस में भी है। नाउ अगेन नेक्स्ट स्पीकर एंड लास्ट स्पीकर, प्रोफेसर एलन मिश्रा, Professor VIT University of Belloro, Tamil Nadu. I request to the delivered lecture, Super Convergence of System of Nonlinear Fractional Volta Integral Equation by Spectral Approximation Method. Professor Mishra, I request again to deliver to lecture.
Good afternoon, sir. Thank you for nice introduction.
Thank you, sir. Thank you.
My slides are visible to all of you?
Yes, sir. Yes,
Yes,
sir.
sir. Yes, sir. Visible, sir.
So, Good afternoon, all. I am very much thankful to Professor D.P. Sukla sir, who has given me opportunity to deliver the talk on superconvergence of system of nonlinear fractional Volterra integral equation in national webinar on recent trends in mathematics and computer science, organized by Department of Mathematics, Computer Science, sponsored by Department of Higher Education, RUSA, and World Bank Scheme, MPHEQIP. So thank you, sir. So these are the contents of our talk. So an equation in which the unknown function is to be determined under one or more integral sign. If unknown function appears only the integral sign, then it is known as integral equation of first kind. If unknown function appear under the integral sign as well as out of the integral sign, then it is known as integral equation of second kind. So equation number 1 is defined as u of x is equal to function of x plus lambda integration from alpha x to beta x k of xt u of t dt. Here k of xt is known as kernel of the integral equation. Alpha and beta are the limit of integrations. Lambda be any non-zero constant parameter. So this integral equation can be defined as non-linear integral equation if unknown functions appears as in non-linearity form, like equation number 2 and 3. Here function of u of t is defined as u to the power n of t for n is greater than or equals to 2. It is defined as non-linear integral equations. If both the limit of integrations are fixed by some constant, then it is known as Fredholm integral equation. If at least one of the limit of integration is variable, then we will say that it is Volterra integral equation. So for example, in equation number 2, it is Volterra integral equation since upper limit of the integration is variable. In equation number 3, both the limit of integrations are fixed by the constant, so it is known as Fredholm integral equation. So here equation number 4 and 5 are known as non-linear Volterra and Fredholm integral equations respectively, since here the unknown functions are appearing in non-linear form. So in 1825, Abel was first produced an integral equation in connection with the famous tautochrone problem. The problem was connected with the determination of a curve along which a heavy particle sliding towards lowest position O. Let us consider a smooth curve situated into vertical plane. The particle starts from rest at point P towards point O. So under the action of gravity, the particle attains potential energy as well as kinetic energy. So in mathematics, we can write half mv square plus mg xi is equals to constant, where m is the mass of particle, vt is the speed of particle at some point q, and g is the acceleration due to gravity, and xi is the vertical coordinate of the particle. So half v square plus g xi is equals to constant c dash, where c dash is equals to c by m, and then we can use the condition v naught is equals to 0 at point P, and hence we can find the constant c dash is equals to g of x, and Abel was produced this integral equation. V is equals to, that is the speed, rate of change of the curve S, and he has established this integral equation 9. So f of x is equals to integration from 0 to s u of xi dxi divided by square root of 2g x minus xi. This k of x xi is called kernel of integral equation. So this is linear integral equation of first kind, which was given by Abel in 1825. So here some definitions and auxiliary facts which will be useful in the proof of our problems for establishing the results. So the on measurable subset I of set of real numbers R with the norm of x LPI is equals to integration of x mod of x to the power p dt whole to the power 1 by p, where p is greater than or equals to 1 and less than infinity. So the concept of norm introduced in order to give for measuring the magnitude of vector quantity. So Banach space of essential supremum is defined as essential supremum of mod of xt, where t belonging to interval I is defined as infimum of A, provided the set T for which mod of xt has greater than A has measure 0. So the norm on X over the L infinity space, that is the Banach space of all essentially bounded functions on I, should be finite. So it is defined as essential supremum of mod of xt for t belonging to interval I. And the space BCR plus denotes the Banach space of all real valued continuous functions and bounded on positive real numbers. So the norm on this space BCR plus is defined as supremum of mod of xt, such that t belonging to positive real numbers. And the modulus of continuity of the function x belonging to the set x and epsilon greater than 0 for positive real number t is defined as wt x epsilon is equals to supremum of mod of xt2 minus xt1, such that t1 t2 belonging to closed interval 0 t and mod of t2 minus t1 is less than or equals to epsilon. And the space of all continuous functions defined on closed interval t naught to capital T over the set of real number r is defined as norm of x is equals to supremum of mod of xt, where t belonging to closed interval t naught to capital T, it will form the Banach space. And the superposition operator is defined as it is measurable in T for any real number x and continuous in x for almost all t belonging to interval I. So it is the function from defined from I cross r to r, that is ff xt is equals to function of t xt for t belonging to interval I. And ff in such a way is called superposition on MST operator generated by the function f. And f belonging to L1 for every phi belonging to phi is defined from interval I to I. The superposition operator generated by the function f and phi is defined as ff f phi f of xt is equals to function of t x of phi of t belonging to interval I. And Urysohn integral operator is defined as a mapping from I cross R to R, which is measurable in Ts for any real number x and continuous in x for almost all Ts belonging to interval I cross I. Then Urysohn integral operator is defined as u of x of t is equals to integration u of Ts xs ds over the interval I. So for arbitrary fixed s belonging to interval I and x be the real number, then the function t on u of t s x of s is integrable. And the multiplication operator is denoted by a of x of t, which is the product of two different operators f and u, where f is superposition operator and u is the Urysohn integral operator. So measure of non-compactness is the main tool used in the proof of our problems. So measure of non-compactness of compact sets gets measure 0 and other sets gets measure bigger according to how far they are removed from their compactness. So a bounded set can be covered by a ball of some radius. Sometimes several balls of a smaller radius can also cover the set. So in fact, we can say that compact set can be covered by finitely many balls of arbitrary smaller radius. So one could ask, what is the smallest radius that allows to cover the set X? So measure of non-compactness are defined mainly in two types: set measure of non-compactness and another is ball measure of non-compactness. So E be the infinitely dimensional Banach space with the zero element theta, and x and convex x denotes the closure and convex closure of the subsets x of Banach space E. And Bxr denotes the closed ball centered at x with radius r, and Br stands for the ball B theta r whose center is origin of radius r, and Me denotes the family of all non-empty and bounded subsets of Banach space E, and Ne indicates its subfamily consisting of all relatively compact subsets of Banach space E. So Kuratowski has defined the set of measure of non-compactness as alpha of x is equals to infimum of epsilon greater than 0, such that x may be covered by finitely many sets of diameter less than or equals to epsilon. And Goldenstein introduced this measure of non-compactness that is known as Hausdorff or Ball measure of non-compactness, as defined as chi of x is equals to infimum of epsilon greater than 0, such that there exists a finite epsilon net for x in Banach space E. So a ball of radius r has diameter at most 2r. So we can find the relation between ball measure of non-compactness and set measure of non-compactness. So since the ball of radius r has diameter at most 2r, so we can find the inequality as ball measure of non-compactness, that is chi of x is less than or equals to set of measure of non-compactness, that is alpha of x is less than or equals to twice of this ball measure of non-compactness, that is 2 times chi of x for any bounded set x be the subset of Banach space E. So this degree of measure of non-compactness of set is measured by means of functions. And this is axiomatic approach towards the measure of non-compactness in Banach space E, which is defined as mu be a mapping from ME to R plus. ME is the family of all non-empty and bounded subsets of Banach space E to positive real numbers R. Then kernel of mu is defined as the collection of all the elements from the family of all non-empty and bounded subsets of Banach space E, provided measure of x is 0, which should be non-empty, and kernel of mu be the subset of its relatively compact subsets of Banach space E. And if x be the subset of y, then measure of x should be less than or equals to measure of y, and measure of closure of x is equals to measure of x, and measure of convex x is equals to measure of x, and measure of lambda x plus 1 minus lambda y is less than or equals to lambda times measure of x plus 1 minus lambda times measure of y for lambda belonging to closed interval 0, 1. So if xn is the sequence of closed sets from family of all non-empty and bounded subsets of Banach space E, such that it is in decreasing order, like xn plus 1 be the subset of xn for n is equals to 1, 2, and so on, and mu of xn tends to 0 when n tending to infinity, then the intersection of the sets x1, intersection x2, intersection and so on will be non-empty. And then this is known as measure of non-compactness. If all these postulates from 1 to 6 are satisfied, then we can say that mu is the measure of non-compactness in Banach space E. And we will say that it holds the homogeneous property and sublinear property if a measure of lambda of x is equals to mod of lambda, measure of x for lambda belonging to real number r, and measure of x plus y is less than or equals to measure of x plus measure of y. It is known as subadditive property. And it holds the maximum property as measure of x union y is equals to maximum of measure of x, measure of y. That is known as maximum property of the measure of non-compactness. And a sublinear measure of non-compactness mu has the maximum property as well as kernel mu is equals to its family of all non-empty relatively compact subsets. Relatively compact subsets means its closure is compact. Then mu is known as regular measure of non-compactness. So since it holds the maximum property, and kernel of mu is equals to NE. So fixed point has major role for establishing the existence of the solutions of various kinds of integral equations. So if f is defined from the set x to x, a point which is invariant under the transformation of the function f is called fixed point. So let us suppose that if y equals to fx be any function, and if we draw a line y equals to x, which is passing through origin with 45 degree with positive x-axis, then we will find some intersection points of this curve y equals to fx and the line y equals to x. So these intersection points are known as fixed points of the function f. And some types of mapping in metric space XD can be defined as T be a mapping from X to X is called Lipschitz map if there exists a real number gamma is positive real number such that d of tx ty is less than or equals to gamma d of xy for all xy belonging to the set X. And T is called contraction mapping if gamma is strictly less than 1, and it is known as non-expansive mapping if gamma is equals to 1. And it is called contractive mapping if d of tx ty is less than d of xy for all xy belonging to the set X and y both are the different element. So Banach contraction principle says that every contraction mapping on a complete metric space has unique fixed points. It guarantees the existence and uniqueness of the certain self mappings. So browser fixed point principle says that Q be non-empty closed bounded and convex subset of Banach space E, finite dimensional Banach space E, and T be a mapping from Q to Q be continuous, then T has at least one fixed point in the set Q. And Schroeder fixed point principle says that Q be non-empty closed bounded and convex subset of Banach space X, and T be a mapping from Q to Q is compact continuous map, then the operator T has at least one fixed point in the set Q. And Darboux fixed point principle says that Q be non-empty closed bounded and convex subset of Banach space E, and V be a mapping from Q to Q be continuous transformation, which is contraction with respect to measure of non-compactness mu. There exists K belonging to closed at 0 and open at 1 such that measure of V of X is less than or equals to K times measure of X for any non-empty subset X of set Q. Then we can say that V has at least one fixed point in the set Q. In 1969, Mir and Killer has established the fixed point in metric space XD, and that is known as Mir-Killer contractive condition, that defined as for each epsilon greater than 0, there exists delta greater than 0 such that d of xy lies between epsilon to epsilon plus delta, which implies that d of tx ty is less than epsilon for all xy belonging to the set X. Then in this inequality is known as Mir-Killer contractive condition, and the function involved here is known as Mir-Killer function. So Mir-Killer conditioning operator is defined as C be non-empty subset of Banach space E, and mu be arbitrary measure of non-compactness on Banach space E, and T be a mapping from C to C is Mir-Killer conditioning operator if for any epsilon greater than 0, there exists delta greater than 0 such that epsilon is less than or equals to measure of X is less than epsilon plus delta, which implies that measure of T of X is less than epsilon for any bounded subset X of Banach space C. And then Mir-Killer established the fixed point, says that C be a non-empty closed bounded and convex subset of Banach space E, and mu be arbitrary measure of non-compactness on E. T be a mapping from C to C is continuous and Mir-Killer condensing operator. Then T has at least one fixed point, and the set of all fixed points of T in C is compact. So by using this fixed point principle, we can establish the results. And a generalized Mir-Killer condensing operator that can be also defined as omega be non-empty subset of Banach space E, and mu be measure of non-compactness on Banach space E, and T be operator defined from omega to omega is generalized Mir-Killer type function if for any epsilon greater than 0, there exists delta greater than 0 such that for any subset X of omega, which shows that measure of X plus psi of measure of X lies between epsilon to epsilon plus delta, which implies that measure of Tx plus psi of measure of Tx is less than epsilon, where psi is the function from positive real numbers to itself, is the continuous function. And omega be non-empty closed bounded and convex subset of Banach space E, and mu be arbitrary measure of non-compactness on Banach space E. T be a mapping from omega to omega be continuous and generalized Mir-Killer condensing operator. Then T has at least one fixed point, and the set of all fixed points of T in S is compact. So here now we can discuss about the existence of the solutions for this functional integral equation, which involve the Riemann-Liouville fractional integral operator given by equation number 11. xn of sigma is equal to fn of sigma x epsilon x of sigma h sigma x of sigma divided by gamma alpha integration from 0 to sigma gn sigma s x of s divided compactness chi in sequence space LP is defined as chi of h is equals to limit p tending to infinity supremum x of sigma belonging to the space H is defined as sigma k equals to p to infinity mod of xk sigma to the power p whole to the power 1 by p. And then H belonging to the family of all undefined and bounded subsets of Banach space LP for p greater than or equals to 1. So now we prove the main result of this problem. For that we have assumed the following hypothesis. When these postulates from H1, H2, H3, H4, H5, H6 are satisfied, then we can say that our integral equation 11 has at least one solution, x sigma, in the sequence space LP for all positive real numbers sigma, and our solutions are continuous from positive real numbers R to R. So for that we will prove that T is continuous operator and then boundedness of the function Tx on the sequence space LP, and then the operator T transforms the ball BR naught into itself, and T is continuous operator on the ball BR naught. And we will find the supremum of I of A, where X belonging to the set A, and then we will estimate the measure of non-compactness W naught of TA, and T is contraction mapping with respect to measure of non-compactness, and hence we can say that our integral equation 11 has at least one solution in sequence space LP. And for the applicability of our considered integral equation 11, we have given the numeric example, which is given by equation number 12. Xn sigma is equals to sigma xn of sigma divided by 7 1 plus sigma n plus sine x of sigma divided by 2 gamma 1 by 2 n cube exponential root sigma integration 0 to sigma cos sigma divided by 5 root sigma minus h ds for n belonging to set of natural numbers. So we can compare equation number 12 to with equation number 11. We can find the functions fn, vn and gn, and hence we can say that all the postulates from H1 to H6 are satisfied. Hence we can say that our integral equation 12 has at least one solution in Banach space LP. So this is, now we will find the approximate solution for our considered integral equation 11 by using the homotopy perturbation method along with a Romian decomposition method. We can provide an efficient iterative algorithm, and we can show that efficiency of our algorithm is better. So here the nonlinear boundary value problem, A of xn minus q of sigma is equals to 0, sigma belonging to the capital sigma. B of xn del del r of xn is equals to 0, r belonging to the set gamma. So A, B, Q of sigma represents a general differential operator, boundary operator together with known analytic functions respectively. So here we have introduced and developed a homotopy perturbation method with parameter P as defined as h vn p is equals to 1 minus p l of vn minus l v naught plus p times a vn minus q sigma is equals to 0. where P belonging to closed interval 0, 1 and N belonging to set of natural numbers. Then L denotes the general linear operator defined as xn sigma is equals to Vn sigma is equals to V naught n of sigma P V1 n sigma plus P square V2 n sigma plus and so on. So V naught sigma is referred to as initial approximations of the solution stated by the initial conditions. So by the transposition of P is equals to 0 to P equals to 1, we can find V naught sigma is equals to Vn sigma to A of Vn minus Q of sigma. And by using the Adamian polynomials, I defined this, Akn of S is equals to 1 by k factorial dk over dp k cos t sigma pj vjn of S divided by 5 times sigma minus S for P is equals to 0. So we have calculated the values of P naught, P1, P2 and so on, Pi's for I equals to 2, 3, 4 and so on. So we can find the approximate solution of our integral equation. So here we have used this MATLAB software for finding the approximate solution of our integral equation. Here some iterative sequence has been defined, first, second, 10th together with 100 terms of the stated sequence, 200, 400 terms of the stated sequence, and sigma lies between 0 to 1. We can find n when n increases the value of xn on vertical axis come closer, and we can say that for any largest value of n, xn sigma approaches to 0 for any sigma belonging to closed interval 0 to 1. So hence our solutions are better. And here we have analyzed the errors and also provided the upper bounds of errors. So another problem is based on this approximate solutions for the nonlinear functional integral equation. Here we have used the Sodor fixed point principle along with Darboux fixed point principle for finding the existence of the solution for the considered integral equations, and also provided the efficient iterative algorithm to find the approximate solution by employing homotopy perturbation and Adamian decomposition method. And the efficiency of algorithm is also asserted. So the space C of I is denoting the family of all continuous functions on the closed interval 0 to 1. And it is the Banach space C01, and AB non-empty and bounded subsets of X belonging to the set A and epsilon greater than 0, then the modulus of continuity of X in the interval I is defined such that mod of phi minus eta is less than or equals to epsilon. And then measure of non-compactness is defined as measure of A is equals to W naught of A plus I of A. I of A is supremum of I of X, X belonging to the set A. And the psi, capital psi is the family, is the set of all functions defined from set of real numbers R to R, which satisfies the following conditions: psi is an upper semi-continuous function from the right, and psi of phi is less than phi for positive real numbers phi. And generalized Darboux fixed point principle says that A be non-empty closed bounded and convex subset of Banach space, and T be mapping from A to A be continuous function satisfying measure of TB is less than or equals to psi of measure of B. For all B be the subset of A, and B be non-empty set for some measure of non-compactness mu, and psi be the element of the set psi, then there exists at least one fixed point in the mapping Q, mapping T. Now we proved the main result of this problem. For that we have assumed these assumptions. So from the hypothesis A1, A2, A3, A4, A5, all these assumptions are satisfied, then we can say that our integral equation 15 has at least one solution in the space of all continuous functions on the closed interval I. So here we can prove that our considered operator is continuous and boundedness of the function Tx on this interval I, and T transforms the ball Br0 into itself, and T is continuous operator on the ball Br0, and we can find a non-empty subset X of Br0 and Xy be the element of the set X. We can estimate I of A is equals to supremum of I of A, and estimated that W0 of T of A, and hence we can show that T is contraction mapping with respect to measure of uncompactness mu, that is measure of T A is less than or equals to side S measure of A. So here we have given the example for the support of our main result. So if we compare the integral equation 17 with integral equation 15, we can find the functions f small f of phi UVW is equals to phi of phi divided by 4 times 1 plus u square plus v plus w. G of phi x of phi is equals to phi divided by 4 plus 1 4 by 1 4 pi by 4 1 plus x square. So when we compare this equation 17 with 15, we can find the functions, and hence we can say that from the assumptions A1 to A5 all are satisfied. Hence we can say that our integral equation 17 has at least one solution in the space C01. Here we have given another example for the applicability of our result, which is given by question number 18. So we can say that it has also at least one solution in the space Ci by using the generalized Darboux-Fixed point principle, and hence we have provided the algorithm to find the approximate solution for our considered integral equation, that is the modified homotopy perturbation method. S of PV is equals to f of phi v minus f1 phi v plus p of n phi v minus f2 phi v is equals to 0, where D is the differential operator divided into two operators m and n, where m is linear or non-linear, but n should be non-linear operator. And we have divided the function f into two of functions f1 and f2. Then this equation number 20 and 21 are modified homotopy perturbation method, the parameter p belonging to closed interval 0, 1. Yeah, sir. So this is, we have used the modified homotopy perturbation method and Elamian polynomial.
Hello, Mishra sir.
Yeah, I am concluding. I am just I will conclude in 2 minutes, sir. So this is the Adamian decomposition method we have found, and here we have shown that absolute error of x1 and absolute error of x2. So, and we have plotted the graphs of v of phi and x of phi. By increasing the number of iteration, we can enhance the accuracy of our solution. So here we have used this software, and then convergence and error analysis we have done that let xk of I equals to sigma I equals to 0 to k vi of I for k belonging to set of natural numbers, and m being inverse with the linear operator. Then this equation is equivalent to algorithm 23, xn plus 1 is equals to m inverse of f1 plus m inverse f2 phi x minus n xn. And C01 norm of x infinity with a Banach space of all continuous functions undefined on closed interval 0, 1. And xn phi is equals to sigma equals to 0 to n vi phi.
Hello.
So norm of vi infinity is less than or equals to alpha, norm of vi minus 1 infinity. So alpha is lies between 0 to 1. So the sequence xn is convergent. So it is enough to prove that xn is Cauchy.
Hello.
Yeah, sir, I'm just concluding. So the sequence xn is Cauchy, it is enough to prove that.
Thank you, sir.
So every convergence sequence is Cauchy, and then we can show that xn converges to x star when n tending to infinity. So this algorithm 23 is equivalent to 19. And then this is the corollary of our theorem, that is norm of x star minus xn infinity is less than or equals to alpha to the power n plus 1 divided by norm 1 by minus alpha, norm of f1 infinity for n belonging to set of natural numbers while alpha belonging to closed interval 0, 1. So these are some references which we have used in our study. Thank you. So
Thank you, sir.
any questions from the participants, they can ask.
Thank you, sir.
Thank you, sir. Thank you so much.
Essential supremum, Dr. Alan Misra, essential supremum you have used. Can you please explain what is essential supremum of function norm f infinity? In infinite norm, essential supremum it is used.
Yeah, sir. Norm x over the L infinity, that is essential bounded functions on the interval I, is defined as essential supremum of mod of xt, which should be finite. So that means it is the collection of the set of the infimum of the set A such that mod of xt greater than A that has measure 0. Then it is defined as essential supremum of mod of xt or t belonging to the interval I. The set is consisting
Yes, yes, yes. Excluding it means yes. Excluding the point of countability, countable number of points exclude.
Yes, sir.
That is jump discontinuity is also countable. So exclude the jump discontinuity point and collect the uncountable points, and that is the essential supremum of that function. Countable set of measure 0.
Yes,
Thank you,
sir.
मिश्रा जी. ये नेशनल
प्रोफेसर मिश्रा
सेमिनार 9 जनवरी और 10 जनवरी को मेरा पूरा हो गया. जो हमारे इमिनेंट प्रोफेसर या इमिनेंट स्पीकर, उनके द्वारा मेरे को स्वयं और जितने पार्टिसिपेंट्स जुड़े थे सभी के लिए बहुत लाभप्रद था. निश्चित ही उसका उपयोग करके वो आगे बढ़ेंगे और हम सभी स्पीकर्स को, इमिनेंट प्रोफेसर जितने हैं स्पीकर्स हैं, सभी का आभारी हूं, क्योंकि अपने व्यस्तम समय निकाल के हमको आप लोगों ने समय दिया और पूरे भारत के कोने कोने से स्पीकर्स जुड़े थे. इसका मतलब ये हुआ कि हमारे पूरे भारत में जितने भी पार्टिसिपेंट्स जुड़े थे सभी को लाभप्रद हुआ और हमारे स्पीकर्स हर जगह से थे. तो हम उनका बहुत आभारी हूं, क्योंकि आज के समय में इतना व्यस्तम समय है कि समय देना बहुत मुश्किल पड़ता है. लेकिन मेरे निवेदन को स्वीकार किया और स्वीकार करने के बाद जितने हमारे छात्र हैं, हमारे पार्टिसिपेंट्स हैं, हमारे कॉलेज के टीचर्स हैं, हमारे यूनिवर्सिटी के टीचर्स हैं, भारत में कहीं भी हैं, सबके लिए बहुत लाभप्रद है. थैंक यू वेरी मच. और आशा करते हैं जब कभी भी मेरी आवश्यकता पड़ेगी फिर से दोबारा तो आपसे निवेदन करेंगे, को समय देंगे. थैंक यू वेरी मच.
Thank you, sir, very much. Thank you.